Now that we know a little bit about how kinematics works in general, we know how position, velocity, acceleration are all related to each other through time, either by taking derivatives or doing integrals. We would like to look at a special case of what happens if our acceleration happens to be constant. Now, of course, this isn't going to be every situation, but man, it is crazy how often cases of constant acceleration pop up. It pops up so much, far more than it has any right to, that it's worth looking at this special case independently and how we can use instances of constant acceleration to make problems a bit more straightforward and less computationally complex. So let's take a quick jump into Mathematica and look at the special case of constant acceleration. Actually, we want Mathematica here. You see Mathematica, but I don't. Okay, so here we are. I've got a case of constant acceleration, and as you know, acceleration is coded in blue, velocity is coded in green, position is coded in red. And as we found in our last video, we could have a constant acceleration that's up here, constant acceleration down here that's negative. Acceleration can be positive or negative. That's totally fine. But if we are to integrate an acceleration over a certain interval of time, it tells us how the position changes. So I look at how to calculate the area under a curve here, and there's not too much that's easier to calculate as far as area under a curve than something like this. This is just the area of a rectangle. So what I see is if I was to double the amount of time that I integrate over, I double the change in velocity. This is what's called a linear relationship. Let's go quickly to the paper here and take a look at what might this look like. So here we see on the x-axis time, here we see on the y-axis acceleration. We're finding area of the curve here. So here I am with paper, and if I wanted to find that change in velocity, the area under the curve, what I'm doing is taking the acceleration and multiplying by the time that I'm integrating over. This is a change in time if you wish. Well, what is change in velocity? Change in velocity is v final minus v initial equals at, or we can say that v final is equal to at plus vi. This is an equation that has the form of y equals mx plus b. This is a line. Now this is a line that could have a positive slope because we could have a positive or negative acceleration. We can have a positive or negative intercept because initial velocity can be positive or negative. But what we find is a line. Now this is kind of a algebraic way of finding out what that is. Let's say we have acceleration equal to some constant. And we know that the velocity is the integral of acceleration over some time. Okay, well I do that integral, this is dt, over some time, dt. I do this integral to get at, but I also get an integration constant. What is this integration constant? This is the velocity when t is equal to 0. If t is equal to 0, the only thing left here for the velocity is what this constant is. So this is v initial. This tells me that the velocity at any time is equal to the acceleration time times time plus the initial velocity. Sometimes I call the velocity at any time v final. These two equations are the same equation. So we can integrate to find it, or we can just look at the properties as we see on the screen. But when I say that this is a linear relationship, a line with positive or negative slope, a line with intercept that is either positive or negative, that's where that comes from. Let's go back to Mathematica. Okay, so we double the integration for time, we double the areas, that's how that stuff all works. But what we're getting is a line, and this line can have a positive or a negative slope, positive or negative intercept. That's the things that we have to determine with our constant acceleration, whatever our constant acceleration happens to be. And we can set v initial equal to 0. We can have acceleration positive or negative. Those are all completely and totally fine. I'll just keep it here for now. But now, if we want to define change in position, what we need to do is integrate over a certain amount of time. And some of these integrals are easier than others. Now clearly this is just finding the area of a triangle, right? Base times height divided by 2. Relatively straightforward. But in the case of a line, as we see here, we can actually look at the average value of initial and final velocity. The initial in this case is 20. The final here is 0. It turns out that the average value of 20 and 0 is 10. I could have had a constant value of 10 over this exact same time interval and done the same thing and found the same area. So there's a couple of ways to find an area under a curve here. One of them is by integrating. One of them is just computationally looking at this. Now this is different. What if these times had been different? Okay, well now we have some triangle that we can find the area of, and we have a rectangle we can find the area of. And we can put those two things together, and that's perfectly and totally fine. But even in this case, if we wanted to find the area that we show here in red, I could have taken this average value of v initial and v final, the average value being right here, and just made a new rectangle that was that big. So there's really two ways to find this area with constant acceleration. So what are we really looking at for this? Let's go back to the paper. So now if we know our velocity as a function of time is at plus vi, we could, over here in this kind of an expression, say that change in position is equal to the integral of vt, right? And what is our velocity? Well, here, there are ways to do that, but we know calculus, right? So why don't we just do this approach here to save ourselves a bit of time? X is going to be the integral of v dt. And we happen to know what our v is. This is the integral of at plus vi dt. And if I integrate this, what I get is 1/2 a t squared plus vit plus an integration constant. What is the value of that integration constant? It is going to be the value of x at t equals 0. At t equals 0, this term disappears. At t equals 0, this term disappears. The only thing left is this constant. This is x0. So this tells me that x, as a function of time, is 1/2 at squared plus vit plus x0, x initial, whatever you want to call it. And x as a function of time is something that I might often call x final. So what we see is x final is equal to x initial plus v initial t plus 1/2 a t squared. Here we are finding change in position. Here we are finding change in velocity. But as I said on the Mathematica, that change in position can also be average velocity, 1/2 v initial plus v final, times time. Because change in x is x final minus x initial, this can also be written as shown here. So if we have constant acceleration, v final is equal to v initial plus at. If we have constant acceleration, v final is equal to x initial plus v initial times time plus 1/2 at squared. And a has all the signs that it needs, v has all the signs that it needs, xi has all the signs that it needs. That's all totally fine. Another way to find x final is knowing our initial x and doing this calculation. Average velocity times time. Totally fine. And these are all true as long as we've got constant acceleration. Something to note about this equation. Now, this equation here, as we already saw, is a linear equation. It looks like a line. This is parabolic or quadratic. In time. We have a t squared, we have a t to the first power, we have no t's. This is a quadratic equation. Quadratic equations make parabolas. So this is parabolic in time. What does something that's parabolic look like? Something that's parabolic, here I'm looking at position as a function of time. This is a parabola. Maybe we start at x0. Maybe we have an initial velocity of 0. Maybe we have a positive acceleration, I don't know, 5. This is a parabola. This is a parabola. We want to see the velocity. The velocity associated with that parabolic position is a line. Okay, so I take the derivative of the line everywhere. The slope of that line was constant. So constant acceleration leads to linear velocity, leads to parabolic position, always. So these positions are parabolic or quadratic in time if you have constant acceleration. Now these three things are all well and good. It tells me how to find final velocity if I know something about acceleration over time. It tells me how to find change in position if I see how velocity changes as a function of time, or if it's accelerating for a certain time, or we have an average velocity over some time. You hear a lot of this stuff with time. What if I don't know how long this took? Maybe I only know that it was accelerating over a certain distance. Is there anything that I could use to make this a little bit easier to look at? Let's try something here. So I have two equations that I want to look at. One of them is v final is equal to v initial plus at. One of them is this x final is equal to x initial plus 1/2 vi plus vf times t. And these are relatively straightforward. I think we would all agree that these are okay, just graphically looking at Mathematica. Let's rewrite this equation as v final minus v initial equals at, or that t is equal to v final minus v initial over a. This is just algebra, but it tells me what t is. Why couldn't I then plug that t in over here? V initial plus v final times t. V final minus v initial over a. Now what I see here is a v final minus v initial times v final plus v initial. this v final minus v initial, v final plus v initial. Multiplying these together, I've got v final squared plus v initial v final minus v initial v final minus v initial squared. That's what this combination is. So what I have is x initial plus v final squared minus v initial squared over 2a. Now I can do a little algebra with this as well. Clearly v final minus x final minus x initial is equal to v final squared minus v initial squared over 2a. V final squared minus v initial squared is 2a x final minus x initial, or v final squared is equal to v initial squared plus 2a x final minus x initial. This is also true if our acceleration is constant. So putting these together, we can create kinematic equations for constant acceleration. The first one is v final equals v initial plus at. The second one, x final equals x initial plus 1/2 v initial plus v final t. The third is x final equals x initial plus v initial t plus 1/2 a t squared. And the final, v final squared is equal to v initial squared plus 2a x final minus x initial. These equations are always true if you have constant acceleration. The acceleration can be positive or negative, it just has to be constant. The initial velocity can be positive or negative, it just has to be constant. The initial position can be positive or negative, it just has to be constant. But these equations are always true if we've got constant acceleration. Now, why do we want this? First of all, constant acceleration pops up all the time. But second of all, what we were doing in the previous video is figuring out how to do problems, how to do integrations, how to do differentiations when we don't know a lot of the details of what the functional form of acceleration, velocity, and time are. This is a specific case where now I don't have to integrate. I don't have to take the derivatives. I just know how the equations are going to work if I have constant acceleration. So very often, unless you are told otherwise, constant acceleration is something that you can hold to. And you can just use these equations. I would suggest that you have these equations written down on your study sheet for the exams. That way you don't have to memorize them. You can just have them sitting in front of you, and you can look at them. And you can start to do analysis and figure out how to work with them and everything else by using this approach. So these are true for all kinematic equations. Now, where are some other places where we see constant acceleration? How common is it? And it turns out it is rather common. One of the places that we see constant acceleration is when looking at freely falling objects. I take something like a ball, like I have here, and I drop it, that is actually a case of constant acceleration. This is a ball that's acceleration due to the gravitational influence of the Earth. It is called the acceleration due to gravity here on Earth, and near the surface of the Earth, the magnitude of this acceleration is called little g. Little g is 9.8 meters per second squared. It's actually a very large acceleration, 9.8 meters per second squared. He's like, oh, well, that's just the acceleration of the Earth. It is huge. It's a huge acceleration. But, that being said, okay, so little g is a special acceleration. And I already know that if I was to take some object and drop it, it's accelerating downward. It went this way. And if this way is the x direction, and this way is the y direction, the ball was going in the negative y direction. It went down. So does that mean that little g is negative 9.8 meters per second squared? Because the acceleration is down. Well, that brings up an interesting point. Because little g is not negative 9.8 meters per second squared. It is positive 9.8 meters per second squared. If you don't believe me, look at the front cover of the book. The electronic version is totally fine. You're going through the notes. You see a positive 9.8 meters per second squared. Depending on the book, it might be 9.81 meters per second squared. Fine, whatever. But you're never going to see the minus sign associated with g. And it turns out that this acceleration due to gravity, the influence of the Earth trying to drag objects down toward it, causing them to accelerate, we all agree that it has a particular magnitude and that it's going to go in a particular direction. The negative sign does not get coded into what the acceleration of gravity is. It is a magnitude and magnitude only. The minus sign comes about because we have an acceleration due to gravity. In our problem, we're going to set up a coordinate system where acceleration is positive or negative. And we can set up a coordinate system where this is the positive direction, or we can set up a coordinate system where this is the positive direction. That's completely and totally up to us. We get to determine that. And if we coded the minus sign into little g, then if we change our coordinate system, now all of a sudden the ball is going to pop up. It's not going to fall anymore, mathematically. And that's clearly not the case. So we don't change the sign of little g, we change the sign of our acceleration. The acceleration is negative, but it has magnitude g, and it goes towards the Earth. So acceleration is a vector. That vector carries a sign. That vector has a magnitude. The magnitude of that vector for freely falling objects is little g. And it has units of accelerations, meters per second squared. And like I said, 9.8 meters per second squared is a lot of acceleration. It really, really is. Now, that being said, not to belabor the point, we're looking at these freely falling objects. How can we use these kinematic equations that we just developed and apply them to an interesting problem, such as one that's associated with freely falling objects? Well, let's look at a couple of examples. One of the examples, this is already done in Canvas, but we can do it here as well. But let's look at the case of a flea. It can jump straight up to a height of some particular height, whatever it is. What we need to find what its initial speed is as it leaves the ground and how long it is in the air. So this is our flea problem. And we have the ground. Great. So here we have the ground. We have some flea. And it goes up to some height, and then it falls and comes down. So what's some of the math? Here is the height that it can go to. What else do we know in the problem? Well, we'd like to see how long it's in the air, and we'd like to find its initial speed as it leaves the ground. But really all we know is how high the flea can go, and that's it. Now the flea is going to have some initial velocity, and we can call it, I don't know, v as it's going up. Sure, it's going to be positive. When it leaves the ground, it's going to be moving up at some final velocity. Is there an acceleration? Yeah. Once the flea is off the ground, nothing is influencing it except the gravitational attraction of the Earth. So the acceleration is minus g. Where does it start? At a height of 0. So using this kind of information, we can go to our kinematic equations. And what are some things that we know? And what are some things that we're looking for? So one of the things we're looking for is, what is its initial speed as it leaves the ground? Okay. We don't know how long it is in the air. Interesting. We need to know how long it was in the air to do a lot of this stuff. And that's one of the things that we're asked to find, but we don't know it yet. One thing that I do know is how high it goes. So if we change these things into y's, v final at maximum height, it doesn't have any velocity in the y direction there. That's where it just stopped and starts to turn around. So its velocity went to 0. If we wanted to look at this in Mathematica, we can do that as well. Let's go here to Mathematica. So we're looking at a problem where the flea is moving up at some velocity. Let's make it a little bit smaller here. We don't know what it is. We just know that it initially has some positive velocity and it has some negative acceleration. When we start the problem, it starts at some height of 0. And I'm just going to put numbers in just to make it look kind of pretty. Okay, so the flea, it's going to go up for a while, and then the flea is going to come down for a while as a function of time. So it has a positive initial velocity, and it has a negative acceleration. Positive initial velocity, negative acceleration. Negative acceleration. Okay. So now as time rolls along, the flea goes up and 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 up until it gets to the top of its motion. What happened to the velocity when it got to the top of its motion? Its velocity was 0. And then it turned around and started to come back towards the ground. It has a negative velocity as it's coming back towards the ground. So even though at the top of its motion it doesn't have any velocity, it does have acceleration. It does have acceleration. It's constant. The acceleration is always there. So there's non-zero acceleration, but there is 0 velocity at that position when it stops and turns around at the top of its motion. Okay, so this is just another description of what's going on here. Let's go back to the flea. So I'm looking at these things, and what I see here, if I wanted to find out an initial velocity, why couldn't we use kinematic equation number 4 that says v final squared is equal to v initial squared plus 2a, I'm going to call it y final, minus y initial. So when I get to the top of the motion, that final velocity is equal to 0. When I start the problem, I'm moving at some velocity v. I add 2, but my acceleration is minus g. Minus g. My final y position is h. My initial y position is 0. I see that 0 is equal to v squared, minus 2 2gh. Or if I wanted to find the initial velocity, that velocity is the square root of 2gh. Now g has units of meters per second squared, h has units of meters, so the argument of this is meters squared per second squared. I take a square root, velocity has units of meters per second. I plug this into my calculator. 2 times 9.8 times 0.44. Take this, take the square root. 2.93 meters per second. That was the initial velocity of the flea as it left the ground. Does it make sense? Well, this is going to be about 6 miles an hour, give or take. And that seems like a reasonable initial velocity for a flea. At least it seems like a reasonable value to me. Okay. Now that was the first thing that we were asked to find, but we're also asked to find out how long it is in the air. And so we go back to these equations. We want to find out how long it is in the air. We could say that the initial velocity and the final velocity are just opposites of each other. That's totally fine. We could say that y final and y initial are equal to 0, and I know the initial and final velocities are related through a minus sign. This fourth equation doesn't tell me anything about time, but I would rather look at kinematic equation number 3 to find out what's going on. And what's kinematic equation number 3 going to tell me? It says that y final is equal to y initial plus v initial in the y direction t plus 1/2 a in the y direction t squared is going to describe this motion. Now, if we're going to find out how long the flea is in the air, it starts on the ground and ends on the ground. So it starts at y equals 0, it ends at y equals 0. Its initial velocity is already something we found, but I'm just going to call it v. Vt. My acceleration is minus g. So putting this all together, I see that 0 is equal to Vt minus 1/2 g t squared. So one way this can be true is to have t equals 0. At t equals 0, the flea is on the ground. That's one of the times when the flea is on the ground. And so I can factor the t out of this. Remembering that we still have this solution of t equals 0, we can also then say that 0 is equal to v minus 1/2 g t. Now algebraically solving this, 1/2 g t is equal to v, or t is 2v over g. This is the time that the flea is in the air. Now, what are the units of this? This is meter per second divided by meter per second squared. This has units of seconds. We pull up our calculator. We've already got this v, so we multiply that v times 2, divide by 9.8. So it looks like about 600 milliseconds. A little more than half a second. That's one way to look at it, but here we've already got this v sort of coded already. If we wanted to, we could have had 2 times the square root of 2gh over g. Another way of writing this would have been 2 times the square root of 2h over g. And what's kind of interesting, now this is basically double the time that it would have taken to get from the ground to the top and going back from the top to the ground again. We haven't really found this 2hg. We could have found it over here if we wanted to, find out how long it takes to get from the ground to that height h, but this is exactly what we would have found. But this gives us some experience practicing and working with two different kinematic equations. Sure, we can do this problem. This isn't so bad. Using our kinematic equations for constant acceleration. We can have positive or negative acceleration if we wanted. We could have positive or negative positions, positive or negative velocities, and there's more details if you were to follow along through the notes in Canvas. What's another problem we can look at? Let's say we also wanted to look at the case of a small rock that is thrown vertically upward with a speed of 18 meters per second from the edge of the roof of a building that has a certain height. Let's use black. We'll get to red a little bit later. So here's our building. It has height h. And we're going to throw a ball that has a parabolic y position. It goes like this. So we're told that at time t equals 0, it's thrown off the building. It has an initial speed, initial velocity that is upward, and it goes up for a while, it turns around and goes down to the ground without hitting the building. So we see motion that looks a lot like this for our rock problem. What are some things that we're asked to find? First, we're asked to find the speed of the rock just before it hits the street. So what are some things that we can do? So I don't know how long it is in the air. I don't know how long it is in the air. We're going to find it later. I don't know how long it's in the air. These first three kinematic equations don't help me. But I do know how the height changes from the initial time to the final time. I know what the initial velocity is. I can find the final velocity. That's totally fine. So let's try to find, using kinematic equation number 4, what's going on. Now this is v final squared equals v initial squared plus 2a y final minus y initial. We don't know what v final squared is, so let's just keep it like this. But our initial velocity is told to us. So we'll plug that in later. This is the v that was given to us in the problem. What's the acceleration? Minus g. What's my final height? 0. What's my initial height? h. Like so. So v final squared is equal to the initial speed squared plus 2gh. And as long as we're not paying too much attention to sign, what this says is that v final is equal to plus or minus v squared plus 2gh. So we could have positive or negative here. Which is it? Well, I know that the rock went up and the rock came down. The final velocity is negative. The final velocity is negative. So I can plug this into a calculator and see what we find. Here's our calculator. Our initial velocity is 18 meters per second. So 18 squared plus 2 times 9.8 times 30 meters tall times 30 is equal to this. I take the square root. So the final velocity happens to be minus 30.2 meters per second. That's what the final velocity is. The final speed is plus 30.2 meters per second because speed is a positive definite magnitude of velocity. Okay, so the problem asks for speed. The speed is the positive of this thing. Here I calculated the velocity. Velocity and speed aren't the same, but the speed is going to be plus 30.2 meters per second. Now we're also asked to find how much time elapsed from when the rock is thrown until it hits the street. And so I pull out my kinematic equations. I know initial velocity, I know final velocity, I know acceleration. I could use kinematic equation 1 for that. Let's do it this way. My final velocity I know from above. Our initial velocity is v. Our acceleration is g. And we're asked to find the time, right? So what I see is v initial minus v final is equal to gt, or t is equal to v initial minus v final over g. We've just calculated the final velocity. I'm going to put the correct sign with that. So this is v final negative. I need to make it negative again. V final was negative, minus a negative is positive, plus 30, plus our initial velocity was 18. There we go. 18 there. So the speed actually changed by 48 meters per second. Plus 18 to minus 30 is what happened. But it's a positive number. Divide by 9.8. The time it is in the air is 4.92 seconds. That's how long it was in the air before it hit the street. Now, is this the only way we could have done this problem? Absolutely not. There's other ways that we could have done it. What if we wanted to find out the time it was in the air first? Because we can actually do that. We were told a lot of things, and the way we would do it is with kinematic equation number 3. It says that y final is equal to y initial plus v initial in the y direction t plus 1/2 a in the y direction t squared. So we're going to end the problem at y equals 0, start the problem at y equals h, have an initial positive velocity of v t, and have a negative acceleration of g. This is a quadratic equation in time. So rearranging terms, I'm going to call this g over 2 t squared minus vt minus h equals 0. So I just pulled everything over to the other side. And this is a quadratic equation where we would normally call something like this a, something like this b, something like this c. The coefficient of t squared, the coefficient of t, the coefficient of t to the 0. And from here we can use the quadratic equation, which would say this. So from this we see that the time is going to be minus b, which is v, plus or minus the square root of b squared, which is v squared, minus 4a, which is 2g, times minus h, 2gh, over 2 times a, which is g. Interesting. There's 2 times here that are going on. And we've got this v squared plus 2gh over g, v squared plus 2gh square root with a minus. What are these 2 times? Let's pull up our calculator. So we've got v squared, 18 squared, plus 2 times 9.8 times h was 30 is equal to this. Take the square root. So this is that argument. Here I took the square root. So this square root of stuff is always 30.2. I'm going to put that and store it in here, because one of these things is positive, plus v initial, which is 18, divided by g. This is the time we saw before, 4.92 seconds. But this is only one of the times. What happens with that minus sign? Well, let's take that thing that we just saved. We add a minus sign to it. And now we add 18. Divide by 9.8. Minus 1.24. So which is it? What does this negative time even mean? It turns out when we started our problem, we were starting at the top of the hill. And we were going through some parabolic motion, but if we go forward in time, we see that the rock goes up and comes back down. It gets down to the ground here. But what if we had started earlier, thrown the rock from the ground at some earlier time and tried to recreate this trajectory over here? It would have taken us it would have taken us 1.24 seconds to get from the ground to here, and then the problem would resume. Because of where we started, what time t equals 0 is, the rock could have been on the ground backwards in time. It wasn't backwards in time because of where we started the problem. But if we had started the problem here, this would have been t equals 1.24 seconds, and this would have been t equals 1.24 plus 4.92, which is 6.1 seconds, give or take. Where did we start? What was time t equals 0? But that negative time really does have significance. If we were to go backwards in time along this trajectory, we would have ended up back on the ground. That's what that negative time means. And now if we have this time, If we have this time, the positive one, we can take that time and plug into all kinds of other things to find out what final velocities are, average velocities, all sorts of stuff that you may want to do. So there's lots of ways to do the exact same problems. These quadratic formulas show up all the time because our position is quadratic in problems like this. So this is just to give us a little bit of an overview of what constant acceleration looks like and how we get to the four kinematic equations. Now, this isn't everything that we're going to do with kinematics. We're going to move into multiple dimensions next, look at things like projectile motion, but we're also going to look at what relative motion is, and we're going to see a little bit about circular motion, but we're not going to delve on it. We're not going to spend a lot of time with it until a unit a little further in the future. But we are going to see a couple of things with kinematics beyond this. But man, knowing how to use these kinematic equations can save you a lot of grief.